Today is the continuation of the same chapter, electric current. Yesterday I discussed about resistance, current, voltage. Resistance depends on four factors I mentioned. It depends on the length. How does it depend? It is directly proportional to the length. Second factor was area of cross section, in other words, thickness. It is inversely proportional to the area of cross section. The third factor was temperature. Fourth factor was nature of the conductor. Nature. These are the four factors which affect the resistance of a conductor. Before we proceed, there is a question which came in the past, and it may come again. The question was like this: a wire is stretched to double its length. What will happen to its resistance? So normally student will think this way: when the length gets doubled, resistance also gets doubled. They will think that the resistance will increase by 2 times, or the resistance will get doubled. But that is the incorrect answer. Correct answer is resistance will increase by 4 times. Why 4 times? Because when you stretch a wire, length increases, but at the same time thickness decreases, or the area of cross section decreases. It becomes half. So it will have the effect of both. It will have the impact of both on the resistance. Length is doubling, so resistance will get doubled, but at the same time area is becoming half. So because of that, once again the resistance will increase by 2 times. That means overall the new resistance will be 2 into 2. That means 4 times of the initial one. That means resistance will increase by 4 times. Similarly, if I say a wire is stretched to make its length 5 times longer, what will be the value? What will happen to its resistance? We say resistance will increase by 5 into 5. Don't write 10. 5 again, one more time 5 will come. So 5 into 5, 25 times it will increase. If the initial value of resistance is 2 ohm, what is the value of new resistance? It is going to increase by 25 times. That is 2 into 25. The answer will be 50 ohm, the new resistance. In ICC, 1 year they had asked this question, somewhere back 2015 or 16. A wire of resistance 6 ohm. There was a wire of resistance 6 ohm which was stretched to double its length. What is its new resistance? The question was like that. What is its new resistance? We know that when we stretch a wire, length and area both changes, so it will have the effect of both. That means the resistance will increase by 4 times, not by 2 times, 4 times. Therefore, the new resistance will be 4 multiplied by initial value of the resistance is 6 ohms. The 4 6 are 24 ohms. So this question is there in the ICC in 2016 or 15, so one of these years. So you please think wisely for the answer of this question. So today we proceed. Yesterday I gave you resistance depends on temperature, but I did not mention how does it depends. So now today you will learn that variation of resistance with temperature. Variation of resistance with temperature. Variation of resistance with temperature. How does it vary? So there are 3 cases over here. We'll write first case. In metals, resistance increases with the rise of temperature. In metals, what are the example of metals? Any metal like copper, iron, silver, aluminium. When we increase the temperature, resistance will also increase. That means directly proportional. So you will be writing the first point. In metals, the resistance increases with the rise of temperature. Now the second point. In semiconductors, such as carbon, carbon, germanium, silicon, etc. Carbon, germanium, silicon, etc. The resistance decreases with the rise of temperature. The resistance decreases with the rise of temperature. When we increase the temperature, their resistance decreases. It does not increase, rather it decreases. That is the second point. Third point, in alloys like constantan and manganese, in alloys like constantan and manganese, comma, the resistance remains constant. The resistance remains constant with the rise of temperature. So that is why we cannot say surely that resistance and temperature whether they are directly proportional or they are inversely proportional or it does not depend. So there are three possibilities and you have to learn the example of each case. In metals, resistance and temperature are directly proportional. In semiconductor, inversely proportional. And the third case, it does not depend on the alloys like constantan and manganese. It does not depend on the temperature. These alloys you can write here. These alloys are used in making standard resistors. In electrical circuit, in electronic circuit, we need resistances. All those resistances which we use over there are made up of constantan and manganese, so that they offer constant resistance. Their resistance should not change with the change of temperature, because the daytime also the temperature fluctuates, temperature varies, and that must not affect the resistance of this constantan and manganese. So that's why we choose these two alloys to make standard resistors. Very often question become why constantan alloy or manganese alloys are used in making the standard resistors. The answer will be that because their resistance remains unaffected or their resistance does not change with the rise of temperature. That is the answer we will be writing for it. Okay. Now about the resistance we have already covered everything. Now the next heading is Ohm's law. Statement of Ohm's law. Right on. It states that the current flowing through a conductor is directly proportional to the Ohm's law. That statement, it states that the current flowing through a conductor is directly proportional to the PD. PD means potential difference. Directly proportional to the PD under bracket we write voltage applied across its ends. PD applied across its ends, provided that the temperature and the other physical conditions are constant, are constant. Therefore, we write on Ohm's law. Therefore, we write current is I is proportional to the voltage. Current flowing is proportional to the voltage. That means more the voltage, more the current, less the voltage, less the current. This is called Ohm's law. And Ohm's law is only valid when temperature is constant and other physical condition means length and area and nature they are not changing. Then only the Ohm's law is valid or applicable. So we write I proportional to V. Next one we write I equal to, this side we are changing the equal side, we multiply by a constant. That constant we multiply what here is 1 by R. So we have the formula I equal to V by R, or this formula very often we write like this, V equal to IR. V equal to IR, like V IR, V. You can read it as V. V equal to IR. So this is the formula we get from Ohm's law. No voltage, no current. More the voltage, more the current, less the voltage, less the current. And that is called Ohm's law. Okay, now limitation of Ohm's law. Limitation of Ohm's law. Limitation of Ohm's law. That means under what condition Ohm's law is only valid, and what is the limitation where we cannot use Ohm's law. Okay, right now it is valid only. It is valid only when temperature is constant. When temperature is constant. You may get one more question on this. Question may come, what is the limitation of Ohm's law? We say Ohm's law is only valid when temperature is constant. Okay. Ohm's law is valid for conductors. Normally all metal conductors follow Ohm's law. All metallic conductors follow Ohm's law. But there are two categories of conductors. One is called ohmic conductor, the other one is called non-ohmic conductor. So we can write on the basis of electricity and the Ohm's law. We have two types of conductor. You can write types of conductors. Number one, ohmic conductors. First one is ohmic conductors. What are ohmic conductors? We say the conductors which obey Ohm's law. The conductors which obey Ohm's law are called ohmic conductors. For example, what is the example of ohmic? As I said just now, that metals. For example, metals like copper, aluminum, iron, etc. They are the example of ohmic conductors. Okay. The same line the VI graph, the voltage current graph, the VI graph, right? The V dash I, the VI graph for ohmic conductors, can be drawn as follows. So we draw the graph to show voltage current graph for ohmic conductor. We write V, and here we write I. The graph will come like this way, straight line. So they are directly proportional. Since they are directly proportional, the graph will come a straight line like this. Okay, normally from the graph we find slope and we find area. We check what is the slope of VI graph determine, what does the slope of VI graph give. Slope means you have to divide this value. I mean y-axis divided by x-axis. That is V upon I into 2. You know the formula V equal to IR. Therefore V by I will be the value of R. R is resistance. Here we can add slope of VI graph is equal to resistance. Slope of VI graph gives resistance. Slope of VI graph determines resistance. Very often they ask this question. What does the slope of VI graph determine? We say it determines resistance of the conductor. And resistance of the ohmic conductor are constant. That's why the line is going straight there, straight. So slope is same everywhere. And its resistance is constant. The conductor whose resistance remains constant, what is the answer for it? We say ohmic conductors. And what does the slope of VI graph gives? It gives resistance. But sometimes the question may come the opposite way. They may say slope of IV graph. Slope of IV. Just the reciprocal of the VI graph is voltage by this. Now let us say I by V. I by V will give the value of 1 upon R, reciprocal of resistance. And that reciprocal of resistance is called conductance. Here we can add conductance. Conductance is the reciprocal of resistance. Here you can add, this means 1 upon R. Conductance means reciprocal of the resistance. So you have to be careful what question is talking about. They are talking about VI graph or IV graph. Usually they will ask about VI graph. VI means V by I. And IV graph is I upon V, just opposite. So I upon V will give the value of 1 by R. That is called conductance. By the way, the SI unit of resistance, you can add on the SI unit here is the SI unit of resistance. Unit of resistance is ohms. That is symbol we write. This is called ohms. This symbol is called omega. And the SI unit of conductance. Conductance is ohm inverse, ohm to the power minus 1. We call it inverse. Minus 1, ohm inverse. Ohm inverse, or we can add per ohm, that is 1 upon resistance, 1 upon R. So that is the SI unit of conductance. Now the second one is right. Second type of conductor is non-ohmic. Non-ohmic conductors. Now second type of conductor, non-ohmic. Now right, the conductors which do not obey. The conductors which do not obey Ohm's law. Which do not obey Ohm's law. Non-ohmic conductors are called non-ohmic conductors. For example, filament of a bulb, comma, diode, D-I-O-D-E, diode. Diode changes AC current into DC current, alternating current into direct current. Diode, comma, transistors, etc. Comma, you can add liquid electrolyte also. Liquid electrolyte, etc. They are all example of non-ohmic conductors. Not obeying Ohm's law is called non-ohmic. Then write the VI graph for such conductors is as follows. So the VI graph will not be a straight line, it will be a curved line. It may be having a shape like this, it may have a shape this way, it may have a shape, zigzag shape, it may have like this, any kind of shape, but zigzag shape it will have. It will not be a straight line, it can have any shape, but in the form of a curve, it not in the form of a straight line. So such a graph is there for non-ohmic conductor, and then previously I drew a straight line, so that was the graph for ohmic conductor. Even question may come, the two conductors are having the graph as follows. They will show two graphs, one with a straight line, one with a curved line, and they will ask you what type of conductors are they. So you see, when the line is curved, it will be non-ohmic. When the line is a straight line, so that will be ohmic conductors. And here the slope of VI graph will be the same, but the resistance will be not constant. Resistance will keep changing. So here we can write variable resistance or dynamic resistance we can call. What does the slope of VI graph for non-ohmic conductor determine? We say it gives the value of variable resistance, variable, because resistance is varying here, variable resistance. So this was about Ohm's law. Now next heading you can give what here is a specific resistance or resistivity. This is also called resistivity, and it is denoted by a symbol like this. First you will be writing like this, and then extend this side like P type, small p type. This symbol is read as rho, RH rho. This is a symbol used for resistivity or a specific resistance. So this is the heading, new heading. First we will be writing here for a conductor, R is proportional to length and R is proportional to 1 upon A, that is inversely proportional to the area. Therefore, we will combine both of them to write R proportional to L by A, multiplying L once L by A. That means directly proportional to it and inversely proportional to the area. Together we write like this. Next line, this sign will change the equal sign by multiplying it with a constant. That constant is rho, like this. Resistivity into L by A divided. Or we write this rho is equal to, making rho the subject, it will become RA by L. So this you can write here where rho is equal to specific resistance of the conductor, or resistivity we call it, resistivity of the conductor. So we write like this. What is the SI unit of resistivity? We'll check. And SI unit of rho equal to SI unit of resistivity or a specific resistance. What is the SI unit of that? We'll check. R is ohm, area is meter square, length is meter. So meter square into meter will cancel. Meter and meter square will cancel. 1 meter will be left in the numerator side. That means answer left over will be ohm meter. Here you can write ohm meter. The SI unit of resistivity is ohm multiplied by meter, ohm meter, from this equation in Icse. And now we'll find the definition of a specific resistance. Right on. The definition we find by this trick, by the applying this method. Area will take unit. Unit means 1 meter square or 1 centimeter square. And length also will take unit. That is either 1 meter or 1 centimeter. That means these two is becoming value getting 1 and 1. The R value will be equal to rho. That is rho is a kind of resistance for which the area of cross section should be unit and the length also should be unit. Unit means 1. So you can write down definition this way. A specific resistance of the conductor, definition you writing, a specific resistance of the conductor, a specific resistance of the conductor is the resistance offered by by its unit length, unit length and unit cross sectional area Okay. Now we will be writing here rho depends on first factor. Rho depends on nature of the conductor, nature of the conductor, and number 2, temperature of the conductor. You can put an asterisk over there, is an important point. Rho does not depend on the length and area of cross section of the conductor. Rho does not depend on the length and area of cross section of the conductor. It does not depend, because length and area, when you take unit, then it's 1 meter fixed length we take, and area also we take 1 meter square, fixed area we take. Then it does not depend on the length and area, rather it depends on the nature of the conductor and temperature. Resistance depends on length and area, but resistivity or specific resistance does not depend on the length and area. If question comes, what happens to the resistivity of a wire or resistivity of a conductor when its length is doubled? We say it remains the same, it does not change. Because whether you make it double or you make it 10 times more and all, but you are going to take the length only 1 meter, you are not considering any other length. So it has no effect of increase or decrease of length on it. I am talking about resistivity. Resistance will be affected, but resistivity will not be affected. So you have to read the question very, very carefully. Whether the question talks about resistivity or resistance. If it is about resistance will change, but resistivity will not change. Or resistivity is also called specific resistance, that is not going to change. So for today we are doing this much. Today's lesson is this much.